name is Brandon Day. I'm a staff applications engineer at Xilinx. Today, I'm going to talk about 1000Base-X over LVDS in Xilinx UltraScale FPGAs. Xilinx supports 1000Base-X in general purpose I/O as well as transceivers. The cool thing about this is that we can transition 1000Base-X applications that used to only be supported in transceivers into general purpose I/O. This enhancement will enable you to save both power and money because of the abundance and low power features of Xilinx general purpose I/O. This opens up opportunities for you to do many channels of 1000Base-X using smaller FPGAs and packages. The IEEE 802.3 covers in-depth physical and logical requirements for building these interfaces. In this demonstration, we are going to focus on the RX and TX Jitter requirements. The diagram shows that at the point 1 of the interface, TJ, or total jitter, is 0.24 UI. At 1.25 gigabits per second, that is 192 picoseconds. In other words, the output of the IC, the jitter cannot exceed 0.24 UI. Now as we move across the channel, we see that at 0.4, the TJ is 0.749 UI, or 599 picoseconds. This is the jitter seen by the receiver. The key site, JBERT M8020A, is set to generate PRBS7 pattern at 1.25 gigabits per second. We then connect this to 85 inches of FR4. This is then connected to an UltraScale VU95 SelectIO receiver. The reference clock is shared between the FPGA's receiver and the JBERT. To introduce the plus minus 100 ppm offset, we change the frequency of the reference clock to the receiver and keep the JBERT at 1.25 gigabits per second. The FPGA receiver clock is now running fast or slow compared to the data. The key site, JBERT M8020A, is set to have an RJ of 20 milliUI. This corresponds to a TJ of 280 milliUI at a bit error rate of 1e to the 12. The DJ portion is generated through Xilinx FR4 trace board. The DCAX scope shows 0.529 UI of DJ. We now turn both on at the same time and see 0.807 UI of total jitter. This means we are exceeding the IEEE specification, proving that we have margin above the requirement. Looking at the BERT screen, we see that we have 1 e to the 12th error-free bits. This is currently a very quiet system, as we can see from the power measurements. Now, let's look at the Xilinx lab tools and turn on the fabric noise with 80% of the flip-flops, BRAM, and DSP utilization. The power has gone up, as we can see, but the error rate has stayed at 0. This shows just how robust Xilinx SelectIO receivers are, and they can handle a more aggressive requirement than the IEEE specification, even with 80% of the VU95 toggling. For the TX measurements, we connect the LVDS output of the FPGA to the DCAX. We can see, still with 80% of the logic toggling, they are easily meeting the TJ specification of 0.24 UI. This demonstration has shown you the value of putting the 1000Base-X interface on Xilinx SelectIO. For more information, please contact your local FAE or visit xilinx.com.